So, speaking about vendor and software, the next speaker is Daniel Geschwender from GC Image that will be speaking about streamlining group type analysis with standard GC GC template through computer vision assisted alignment.
Thank you. Hello, I'm Daniel Geschwender. I'll start my talk by giving an overview of the type of template-based methods we'll be considering. Then I'll go into a little more detail on our proposed workflow for retention time alignment, which will involve a peak matching step based on visual matching of the local chromatographic patterns. Then we'll compute a transformation to perform the alignment. And then finally, we'll do some verification on the resulting groups, again, using chromatographic patterns. Hydrocarbon type analysis is an important type of characterization for petroleum products. It can be used to optimize production operations and for quality control, and as well as to meet various government regulations and environmental standards. So traditionally, methods for hydrocarbon type analysis have been based on one-dimensional gas chromatography, but there are some known limitations with this from overlapping hydrocarbon types, so especially the C9 and heavier compounds. So as we know, 2D GC can help with that by offering greater separation capacity. So a first example here we'll consider is a simple GC GC analysis, which has some similarities to the 1D GC ASTM D8580. So in this, we're wanting to identify some specific peaks, benzene, toluene, ethylbenzene, as well as determining a retention time region of the C9 and heavier aromatics. With a GC-GC analysis, we can get a little more detailed in the type analysis by breaking this region down even further into more granular regions. But to perform this analysis in an automated way, we need some kind of tool to represent these different components of the peaks and regions. And so in the GC image software, we refer to this as a template. So a template allows the recording of peak locations by retention time, as well as any associated information, the spectra and so on. We can also record the chromatographic regions defined as polygons over the retention time space. And these will enclose the compound groups of interest. We can also specify various chemical logic expressions, which can be used to impose constraints on our peak matching algorithms or to compute various quality assurance metrics. And then finally, we can attach all sorts of other various metadata, descriptions, other chemical properties, and so on. So with that in mind, there's a couple more standards we'll consider that we can apply a template to. So the ASTM D8396 involves identifying 42 different reference peaks, and as well as identifying regions for the paraffins, naphthenes, 1-ring, 2-ring, 3-ring aromatics. And then similarly, UOP 990 involves identifying specific peaks and regions. In this case, it's a more complex template is required, involves matching 90 different peaks and hundreds of retention time regions. So as you can imagine, that would be a very time-consuming process if done by hand. So we would like to be able to handle that in an automated fashion, but the difficulty is that you cannot just take the template, align it once, and expect it to work from there on out with all of your data. You're going to need to do periodic updates to that due to retention time variations that can occur. So these can occur from just run to run, systematic variations due to pressure and temperature fluctuations or aging of the system. So even just within a same system, you can have variations, but across systems, then if you needed to transfer that template across data acquired from various different systems, there'd be even larger differences to account for. So in this first example here, we have a single distillate sample, which was run 4 different times on the same system over a period of about 2.5 years. And so there are some significant shifts in the peak locations after that 2-year period. In this next example, we have a single distillate sample that was run consecutively multiple times just over a period of 3 days. So just repeated runs on the same system also yields some retention time shifting. So it is going to be necessary to measure that retention time shift and correct for it in our analysis. And so typically the procedure, the data processing procedure used in these types of methods involves analyzing a reference sample, verifying the responses against the method, analyzing several unknown samples, and then quantifying those responses. And so at each of these analyzing steps, we may need to perform a retention time alignment following these steps, loading the standard template, identifying the reference peaks that we're looking for, and using those to transform the template, and then finally performing verification on the resulting boundaries. So ideally, it would be nice if the data processing software was able to help with this process either entirely or if manual intervention is necessary to smooth that process as well. So we are proposing performing a peak matching using the local chromatographic patterns of peaks and using a vision-based approach to match those across chromatograms. And so that's similar to what would be done manually by an analyst in the absence of spectral data. You would just rely on pattern matching to identify the correspondence between these peaks. So if we can automate that same logic, that would be very useful. So specifically, we are using the enhanced correlation coefficient, which is a measurement of image similarity from the field of computer vision. And it has the nice property of being invariant to photometric distortions, such as lighting and contrast in the context of natural images. But in our context, that helps us handle the intensity variations that will occur. And so we compute this ECC score through a number of different variations based on looking at the local regions around a peak at different zoom levels, so different scales of the surrounding, as well as different value mappings, logarithmic, linear, and exponential mappings of the values to the pixels that we're considering. So here are some examples of some of those variations that we're looking at, different zoom levels and such. And so we would like to evaluate the performance of this ECC metric in identifying the correct match. So we took 166 different chromatograms with 7,600 individual peaks, which we manually matched between the reference and the sample. And we computed the ECC metric on each of the peaks to be considered between those peaks and any potential candidate matches. And we ranked those scores, and we found that 82% of the time, the correct match was identified as the top scoring hit. 92% of the time, it was within the top 5, and 95% of the time, it was within the top 10. And so even if it wasn't able to identify as the top hit the correct match, within the returned hit list, it would still generally would find the correct hit, and so that would aid in any manual corrections that needed to be made. But more importantly is that it's important to note that we don't need this to get 100% accuracy, because this is operating purely visually. It's not accounting for the retention time, location, or distance between the peaks. There are peaks that this just isn't going to work for. For example, the N-paraffin series, each of those individual peaks, if you were to look at a zoomed in view of that peak, you would not be able to distinguish that visually from any of the others nearby in the series. So what we want to achieve with this is being able to identify a certain number of very distinctive peaks that we can match visually. And then from there, we can use those to kind of anchor the rest of the transform and use retention time locations and distances to kind of nail down the rest of the matches. So we compute a confidence score in how likely we think that the top match is actually correct, based on just the raw score itself, as well as the scores of alternative matches. And so we can set a threshold of where we want to cut that off and actually assign the match. And so if we set the threshold at 0.9, we ended up getting 40% of the peaks matched with nearly 100% precision. So that allows us to get a handful of peaks as a starting point. And from there, we can incorporate further retention time information and distance scores. So we applied that to a few examples. Here I am showing an example of two chromatograms following the UOP 990 standard. And so we are attempting to transfer the template from one to the other. These chromatograms were acquired from different labs, so there's a certain amount of visual difference between them. And so with our matching algorithm, we were able to match a good portion of the peaks correctly. There were still some that were left unmatched that needed to be manually corrected. So the match scores that we computed helped with that manual matching process by giving easier access to good potential candidates. We also considered a second case where we have two UOP 990 chromatograms acquired from the same lab. So this would be more representative of kind of a periodic update of the reference to account for any shifting that had occurred. So because these were acquired from the same lab on the same system, the chromatograms were much more similar, and we were able to match automatically almost all of the peaks. There were still a handful that needed to be corrected, and again, the scores provided helped speed that process. So once we have all of our landmark peaks matched, we can compute a transform function to transform the retention times from one chromatogram to the other. And so this can take the form of a global transform function, which would be a single function computed over the entire chromatogram and kind of a best fit match for all of the individual matched landmark peaks. So this could be like an affine or second order polynomial function. We could also consider a local transform, which would be a combination of many functions that is kind of locally weighted to each of the matches in a local region. So we ended up using a combination of global and local transforms. And so we transformed the template regions and applied the regions to the chromatograms. And finally, we wanted to verify those resulting group boundaries. And so again, we can use computer vision for this. So we take the corresponding groups between the reference and the sample chromatogram and take the enclosed data and do a visual comparison using the same metric we'd been using previously. And if the score is below a certain threshold, we can highlight that as an area for potential manual investigation or correction if necessary. So on the interlab case acquired between two different labs, we have a fair number of highlighted regions that are flagged for manual verification. With the intra-lab case, there are just a handful of regions to be checked out manually for further verification. So with this computer vision technique, we can match landmark peaks based on their chromatographic pattern, and we can use that then to compute a retention time transform. This allows us to take a standard template and fairly easily transform it to a reference chromatogram acquired by a lab. And then as a periodic update to this, we can take that same standard template and retransform it to any newly acquired reference by that same lab even more easily. And so a lot of this process can be automated in the parts that do require manual intervention. The matching scores that we compute are great help in aiding the analyst in performing those manual steps. So with this, we hope that a routine retention time alignment workflow is possible by combining these tools. So I'd like to thank you for your attention, and I'd be happy to take any questions.